Look at the internal architecture of this quantum processor. Engineers manage a dense network of thick, multi-layered cables that completely dominate the machine's physical footprint. The goal is to take this massive computational power and shrink it to fit onto the same silicon chips used in today's electronics. This scaling is the only path toward integrating quantum technology into pocket-sized electronics. Right now, a physical barrier stands in the way. We can make the processor smaller, but we lack a reliable way to connect those microscopic bits together without reverting to bulky macro-scale wiring. Shrinking these computers requires a microscopic method for the individual parts to transmit information. Researchers are focusing on the Magnon, a tiny wave of magnetic energy that travels through solid materials. Operating at the nanometer scale, it easily talks to particles like photons and phonons. This makes it an ideal quantum bus for carrying data between systems. But the technology has been held back by a consistent failure. Magnons vanish almost as soon as they are created. Most of these waves decay within a few hundred nanoseconds, a window of time too short to perform any useful computation. This raised a question for the physics community. Are magnons short-lived because of an unbreakable law of nature, or simply because our laboratory environments are too chaotic? A team at the University of Vienna set out to challenge that lifespan limit. They identified the primary cause of decay: physical defects on the outer surface. As wide magnetic waves travel, they scrape these jagged boundaries and break. To fix this, the team excited compressed short-wavelength magnons that travel straight through the crystal's dead center. While the structural change protected the waves from surface collisions, they still faced interference from ambient heat inside the material. By successfully bypassing the surface defects, the team proved the Magnon's lifespan could be extended, giving them the confidence to address the temperature problem. The researchers used ultra-pure spheres of yttrium iron garnet to house the magnetic waves. They placed these spheres inside a mixed-phase cryostat to reach temperatures colder than deep space. The system reached 30 millikelvin, just a fraction of a degree above absolute zero. This extreme cold freezes the thermal processes that normally scatter delicate magnons. By combining the compressed wavelength with near absolute zero temperatures, the scientists created a pristine environment to see exactly how long a magnon could survive. The results exceeded all previous records. The magnon survived for 18 microseconds. Compared to the old limit of a few hundred nanoseconds, this represents a 100-fold increase in the wave's lifespan. The team tested 3 different crystal spheres of varying quality and found a direct correlation. The purer the material, the longer the magnon survives. This indicates the remaining limit on the wave's life isn't caused by a law of physics, but by minute trace impurities still hiding inside the crystal. Extending the life of a magnon is now a matter of refining material science rather than discovering new physics. At 18 microseconds, a magnon is no longer a fleeting signal, it is a reliable unit of quantum memory. Because magnons can interact with light, sound, and electricity, they can serve as universal translators, linking different quantum systems together on a single chip. This provides the quantum bus needed to connect hundreds of qubits across a shared path, a necessary step for building a scalable computer. While significant engineering hurdles remain in cooling and error correction, the creation of a long-lived quantum bus proves the barrier of internal communication is finally coming down.